Hey guys, so I've got two integration techniques left to teach you before you can move on to Calc 2. Um, the first one that I'm going to start with is integration by parts because it's more fun, which means it's way more complicated. So if you pause the video for a second and take a look at these three, you'll notice there's no way for you to integrate them right now. Even with arguably your most powerful integration technique, U substitution, you can't, that won't do anything with these three examples because none of the pieces are the derivatives of the other pieces. So there's no way to fudge and fix anything to make this work. What we are going to do is parts, which is basically a backwards version of the product rule. Now, instead of just throwing the formula at you, I want to show you kind of where it came from so that you have an idea of how it works. Let's say, sort of like with U substitution, instead of using F and G or anything, I'm just going to use U and V. Let's pretend you had a function that is two pieces, and again, instead of calling it f of x and g of x, I'm just going to call it u and v for simplicity. Now, if I want to take the derivative of u times v, then I have to use the product rule. So I will leave the u alone and differentiate the v part. And then I will leave the v alone and then differentiate the u part. Now let's undo everything I did. So I just took the derivative of this. Let's integrate that. Obviously, the integral of the derivative of uv is going to go right back to being just uv. And on this side, I'm just going to say this is u, and v prime I'm going to write as dv, and u prime I'm going to write as du. Now there's actually a little bit more going on here with dx's coming in and getting canceled out, but I don't need to get into the nitty gritty. This is basically what's happening. And now I'm going to just rearrange this and solve for this term right here. So the integral of u dv is equal to just uv minus, imagine I'm just subtracting this over to the other side here, minus the integral of v du. I know that looks weird, but that is our integration by parts formula. So if we can get our integral to look like this, then we can expand it into this. Of course, this side still has an integral involved, but we're hoping that that integral is going to be easier for us, or even possible for us to integrate, as opposed to the one that we started with, which was this one. So this integral might not be possible to integrate, but if we can expand it into this thing that looks bigger and uglier, it might be possible to evaluate. So here's an example. Let me just jump into an example. Kind of like U substitution, you have to decide right at the beginning what your two pieces are. If you're going to apply integration by parts, you need a u and a dv. And you have options. You can either let x be your u, or log x be your u, and that means the other one's going to have to be your dv. The general rule of thumb is that you want to make, most of the time, you want to make the part that gets simpler as you differentiate. You want to make that part u. However, that's not the case here. If I don't want to make this video too long, so I'm not going to go down the other road here. I'm just going to, spoiler for you, we're going to let u equal the natural log of x. And that means that dv is going to have to be the x part and the dx. The dx is always going to get attached to the dv part. If I just back up for a second, I can't do it the other way around because I'm going to have to, from u and dv, come up with v and du. So I'll differentiate u to come up with du, and the derivative of log x is 1 over x dx. and the integral of x is 1/2 x squared. Don't worry about the plus c here. So again, if I back up a little bit, letting u equal x would mean that dv had to be log x. And I don't know if you realize this, but you don't have an integral rule for log x. You can't integrate that. So I could never have let this be log x, because then I would never have been able to come up with a v. So that's why my hands were tied and I had to let u equal log x and dv equal x. So again, from the integral, you decide what's going to be u and what's going to be dv, or what's going to be dv and then the other part has to be u. The dx part always goes with the dv. Once you've made those decisions, then differentiate u to get du and integrate dv to get v. And then we have everything that we need to expand this into these two terms. So here's my u, and here's my u, and then this part is my dv, so I have an integral that is in terms of u dv. So this gets expanded to u times v, which is going to be 1/2 x squared times log x minus the integral of v times du. So here's v and du, and I'm going to have 1/2 x squared times 1/x. That's just going to give us x, and this dx will be my infinitesimal here. Now I still have an integral and I still have to evaluate that integral, but this integral is possible to integrate. This one wasn't without doing all of this work. So this integral is easy enough for us to use our backwards power rule on, and I can just make that 1/4 x squared, and now I'll throw on a plus c. You can factor out a 1/4 x squared if you want, but you do not need to do that. So there you go, there's integration by parts. Okay, I'm going to come back to these two examples in a couple of minutes because they're going to get a little bit weird. So let's do a couple more of the simpler examples before we jump into those. Here's another example of an integral that doesn't work, that u substitution doesn't work on. So we're going to have to break it up into two things, a u and a dv. Now this is where our general rule is going to work out for us. The part that gets simpler as you differentiate is going to be our u, which is the x. X goes to 1, then 1 goes to 0. If I keep integrating it, the terms get simpler and simpler. If I keep differentiating the e to the x part, then it just turns into e to the x, and then e to the x again, and then it stays e to the x forever and ever. It doesn't get simpler. So we're going to try to let u equal x, which means du is just dx. Once we made the decision for u, our decision for dv is made for us. It just has to be the rest of the integral. So dv is going to have to be e to the x dx. And then I'll integrate that to get v, which is just e to the x. Again, we don't care about the plus c right now. Okay, so then we're just going to fill in our formula. This whole thing expands to u times v, which is x times e to the x, minus the integral of v du, which is e to the x times dx. And this is an integral that you can handle. We couldn't handle it really without doing all this work the way that we started, but this integral is simple. The integral of e to the x is just e to the x, so x e to the x minus e to the x. Now we'll throw on our plus c and we're done. Again, you can factor out the e to the x, but you really don't have to. So there you go. Okay, I mentioned before that we don't actually have an integral rule for log x. And so that made me want to go ahead and jump in and maybe try this example. Let's try to take the integral of log x and see what happens. I know it looks like we only have one piece here, but we can still use integration by parts. There are two pieces here. There is a log x and then there's a 1 dx. So I'm going to try integration by parts and we're just going to see what happens. like our first example, the log x has to be your u because you don't have a natural integral rule for it. So I'm going to have to let u equal log x, which means the dv part is just the 1 dx. The integral of log x is 1 over x, and the integral of dv is just going to be x. Excuse me. So there we go. I let u equal log x. That means dv just has to be the rest, which isn't a lot. It's just a little dx. Differentiate u to get du, integrate dv to get v, and then you have everything that you need. So this expands to u times v, which is x log x, minus the integral of v du, which is, well, the 1 over x and x cancel, and you just have dx. Simplest integral on the planet. X log x minus x plus c. So now you actually do have an integral rule for just log x. You can have that memorized now, or you can just always use integration by parts when you have to integrate log x. Okay, so I've got a couple more examples I want to get through, and these can get a little bit weird. So you'll see what happens in a second. I think we're going to need a little bit more room, so I just moved the one part of the formula that we need up here so we can cheat off of that. All right, if we take a look at this one, our general rule of thumb again is that if we have a piece that gets simpler as we differentiate, that's probably what we want to let u equal. So I'm going to pick the x squared as my u, because if I keep differentiating it, it goes to 2x and then 2 and then 0, 0, 0. It gets simpler. The e to the x thing just stays e to the x forever. So u has to be this thing, which means dv is e to the x. Remember that the dx always goes on the dv part, and now we're just going to differentiate this and integrate this, and then we have everything that we need. So let's just expand this thing to, and I'm just going to, actually, I'll just jump down here. This thing becomes u times v, so that's going to be 2x, I'm sorry, what am I looking at the wrong thing? U times v, this x squared e to the x, minus the integral of v times du, so that's these guys, 2x e to the x dx. Okay, now here's the problem. This integral we still can't handle. Use substitution is not going to work on it. It kind of looks like we need to use integration by parts. That's exactly what we're going to do. Sometimes you have to use parts more than once so that you can eventually get to an integral that you can handle without using parts. So everything else, please just don't forget everything else on the left that we've already calculated has to come along for the ride. We don't just throw this piece away. So just to handle this integral, I'm going to go off to the side again and come up with a new u and a new dv. And here's the thing, if you're going to do parts twice, whatever piece you let u equal before, you have to let that same piece be u this time. I'm not saying I'm going to let it be x squared, it's going to be the 2x piece, because the x squared turned into the 2x. I guess it's the polynomial part is what I let be u before, so the polynomial part is going to be u this time. I can't switch roles and let u be the e to the x part and the dv be the 2x part. I'll leave this to you if you want to try this. If you do that and you switch roles, you're going to wind up with the integral that you started with, and that's not what you want. You're just going to undo everything that you've done so far. So let u continue to be the polynomial part, 2x, which means dv has to be the rest of it, e to the x dx. Okay, differentiate this guy and integrate this guy. And then you're just going to use your formula again. But please don't forget to bring all of this work you've already done along for the ride. And also be careful, you were subtracting this integral, so now you are going to be subtracting this whole expansion. This integral becomes two different things, so I usually open up some brackets so I don't forget to distribute the negative on my next step. This integral becomes u times v. So what's that? 2x e to the x minus the integral of v du, which is 2 e to the x dx. Now that's an integral that we can do. I mean, you can just imagine that factoring the 2 out, the integral of e to the x is e to the x. So we're done. Let's just distribute the negative, integrate the e to the x, and then we're done. So we've got x squared e to the x minus 2x e to the x plus 2 e to the x plus c. So there's an example of possibly needing to use integration by parts more than once on a single problem. You can actually use it 3, 4, 5, 20 times on a single problem, although hopefully you won't have to use it 20 times. Stay tuned for a few more minutes. I'm actually going to give you a shortcut. If you feel like you're going to use integration by parts more than once on the same problem, there is a sort of a shortcut. It's called the tabular method, and I'm going to come back to that in a couple of minutes. All right, the last of our 3 original problems here. This one is going to be a little bit weird because there is no piece that gets simpler as we differentiate. E to the x keeps on going to e to the x. Sine goes to cosine, which goes to negative sine, which goes to negative cosine, which goes to sine, and it just keeps bouncing back and forth between sine and cosine, and sometimes it's negative. It definitely never gets simpler. So it kind of doesn't matter what you pick to be u. Doesn't matter. You can go either way. I'm just going to let u equal the e to the x part, because who cares? Now, sometimes it's not obvious what you pick, and you can pick the wrong thing. Sometimes it really doesn't matter, and it will work out no matter which way you go. Sometimes you will make things worse. You'll recognize that, and then you'll just back up, switch roles, and try it the other way around. But here, it really doesn't matter which one you let u equal. So if u is going to be e to the x, then du has to be the sine part. And of course it gets the dx. The derivative of u is e to the x dx, and the integral, sorry, that should be a v. The integral of that is going to be negative cosine. Okay, so let's just expand this. This is going to be u times v. So we have negative e to the x cosine x minus the integral of v du. So I'm just going to use the negative out front, turn that into a positive, and I have e to the x cosine x dx. All right, this kind of looks like the last example because we have an integral that doesn't really seem any simpler, and it kind of looks like we need to use parts again. So that's what we're going to do. And just like before, we're not going to reverse the roles of anything. The exponential part was my u before, and it's going to be my u this time. The trig part was my dv before, so the trig part's going to be my dv this time around. So let's just go over here, and we'll say u equals the exponential part, and dv will be the trig part, cosine. So du has to be e to the x, and then v would be sine x. Everybody good? So let's see, we'll bring all this along for the ride. And then I'm going to expand this integral into u times v, our new u and v, so that's e to the x sine x minus the integral of v du, which would be just e to the x sine x, right? Okay. Well, now it looks like we have to use parts again. But if you do that, a few more times, you'll realize this integral, the integral that shows up in, as the integral of v du, it's never ever going to land on something that you can integrate with any other rules that you have. But notice what just happened. I expanded the integral of e to the x sine x into a bunch of junk that includes an integral of e to the x sine x. I can actually add this whole integral to both sides of this equation. If you think of the, I didn't keep writing this, but the left side of this equation is still this. And we have like terms. So I can actually add this integral over to the left-hand side to get 2 times the integral of e to the x sine x equals all this stuff. So, to solve for the integral of e to the x sine x, I'm just going to divide by 2. And just chuck a plus c on there, even though you didn't actually integrate anything. So that's a really bizarre example of using integration by parts twice, landing on the integral that you started with, and then thinking to combine those integrals because they are like terms, and then just dividing both sides by 2, and then there you go. Without even integrating, you've got your answer. All right, the last thing here is that I wanted to show you the tabular method. It's sort of a shortcut. If you know that you're going to have to, or if you get the sense that you're going to have to use integration by parts more than once, then you might want to sort of do all of the u, dv, du, v work off on the side really quick once, and then you can just sort of go right to your answer. So I'm pretty sure if we do integration by parts the way we've been doing it, I'm going to let u equal x to the 4th. And then I'm going to wind up with an integral that involves 4x cubed. And probably a sine or something. But I'm still not going to be able to integrate that. So the next iteration of integration by parts is going to wind up having like a 12x squared and a cosine. And I'm still not going to be able to integrate. So I'm going to do parts again. And I'm going to have to do parts one more time, I think, after that. And then maybe I'll have something that I can integrate. Instead of doing those 4 things off on the side every single time I have to restart over integration by parts, I'm just going to bang it all out really quick off to the side one time. So pick whatever piece you want to let be u, which again is usually going to be the piece that gets simpler. X to the 4th goes to 12x cubed, which goes to 24x, which goes to 24, which goes to 0. That's an example of a piece that's getting simpler as we differentiate. The cosine just bounces back and forth between sine and cosine and sine and cosine, and sometimes it's negative and sometimes it's positive. That doesn't get simpler. So this only works if one of the pieces eventually goes to 0. So pick the piece that goes to 0. Here are all of my u's. Let's start with x to the 4th, and then it becomes 4x cubed, and then 12x squared, and then 24x, and then just 24, and then 0. So pick your u value and then differentiate it all the way down to 0. Again, this only works if one of the pieces actually gets to 0 if you keep on differentiating. Now, pick your dv. That's going to be my cosine part. And just integrate that straight down the side here. So cosine came from sine, sine came from negative cosine came from negative sine came from cosine, and cosine came from sine. Let me just make sure I got all those signs right. Sine to cosine. Looks good. Okay, cool. Now the other weird thing is because of that, Yeah. Because of that minus sign right there, I want to start with positive and then alternate my signs. Because basically it's because we're subtracting this integral, so alternating the signs down here on the left is basically us distributing that negative through. Okay, so start with positive and then just alternate signs all the way down. And then you're going to match up the pieces. This u is going to wind up going with this dv, and this u with this dv, this u with this dv, this one with this one, and this one with this one. So we wind up not really using the first dv or the very last u. Anyway, our answer is sitting right in front of us now. I'm just going to put these guys together. And we have x to the fourth sine x plus, because these are both negative, so it's going to be plus 4x cubed cosine x minus 12x squared sine x minus, I'm going to have to go to another line here, sorry, minus 24x, and what was that, cosine, and plus 24 sine x, and then just chuck a plus c at the end there and you're done. So you don't really even have to, I mean, I guess we integrated this all the way down, but not a whole lot of integration to do, and you're all done. So you bang out all of your u and your dv stuff on the side once, alternate your signs, and then you just match up your u's and dv's, put them together, and you got your answer. We'll do one more shorter example of that, but that's it. That's your tabular method. If you think you're going to wind up using parts more than once on the same problem, just use the tabular method. Okay, here's your very last example. I'm going to use integration by parts more than once, and I have that feeling because I see an x squared. So anytime you have a polynomial part that will differentiate to 0 eventually, it's probably a good opportunity to use tabular. And it takes more than one step for it to get to 0. That's my hint that the tabular method is probably a good idea. X squared goes to 2x, and then to 2, and then to 0, so it's going to take a few steps to get there. So let's just do all the work over here real quick. U is going to start out at x squared, and then it becomes 2x, and then 2, and then 0. So the dv starts at sine 2x, and if I integrate that, it's going to be negative 1/2 cosine 2x, and then negative 1/4 sine of 2x, and then 1/8 the cosine of 2x. Technically, there's a little u substitution going on there. Hopefully, I know it's been a while since we've integrated this kind of stuff with all the AP break that we took, but if you differentiate from here up, you should see what's happening. That's how the 1/8, the chain rule makes the 2 come out here, makes that a 1/4, and then this 2 comes out and makes it the 1/2, and so on. Just trust me, those are the integrals. Anyway, we are going to alternate signs, starting with positive, and then we're going to match up those terms, and that's going to be our answer. So we have negative 1/2 x squared cosine 2x plus 1/2 x sine 2x and plus 1/4 cosine 2x. And running a little on space there. Don't forget plus c. And there you go. That's the tabular method. So now you can try the homework that's posted on Classroom. It's also in Genesis. And just reach out if you have any questions whatsoever about this technique. All right, good luck, guys.